Good morning to all and welcome to the third lecture, which is on the finite element method. I would say this lecture is the crucial lecture of this module, where you see for the first time how the finite element method actually works behind your computer. So let's start immediately. I will just, as usual, become small and little over here and bring my laser pointer out, and here we are. So the finite element method, well, again, let's consider our potato that is as with a sign displacement on SU with volume V, a surface SF where surface forces are applied and body forces, capital F, on our volume V. The finite element method in the end of the day combines two main ideas. Okay, the first is the introduction of a way to describe a continuum body, okay, how it deforms by means of a model for the displacements which satisfies the kinematic compatibility. In a sense, we want to find a way to describe the displacements inside our body through a model with a finite number of unknowns. And in order to do that, well, again, I just introduced this hat to remember that they have to be kinematic compatible displacements. So also the model must be kinematically compatible. And to have a finite number of unknowns, then we have to subdivide the volume V by a finite number of smaller portioned finite elements. In the end, we can reassemble, by knowing the behavior of each element, back to the total volume and structure. Okay, so the outline of this talk is basically covering the essential steps that characterize the finite element method. Namely, these are: we need an idealization of the problem, so the real physical system, so a building, a beam, etc. We have to idealize it. Okay, we need to discretize, number two, our continuum body, as we've seen, for example, in the simple circle and calculation of pi in the introductory lecture. We need a model for these displacements, and we'll see that. Then sometimes when the global reference is not the same as the local reference of my finite element, we need to do some transformation. We'll see that. After that, we can assemble our solution and then impose equilibrium in a discrete form using the stationarity of the total potential energy. Given that, we will get a final equation that is a linear system that can be solved. To solve it, we need to play a little bit with the matrix, because you will see some nodes are free, some are not, because there are boundary conditions, etc. Once we have the solution of the system, we can reconstruct the whole set of unknowns: stresses, strains, and displacements. Okay, so let's see each of these points one by one. And so open your ears and follow properly, because this is sort of the core of this module. Well, the idealization is basically what engineers do every day. So structural engineers or analysts or people that design structures, and that basically need to, given a real structure or a real project, for example, this is a render of our beautiful VNA in Dundee, how do we determine what sort of beams and the foundations, etc., what are the loads within our structure? Well, we did a numerical model of this, but to pass from the architect drawing, beautiful drawing, to the model, a finite element model, we need to idealize our geometry, real structure, by introducing, schematizing external loads, the material behavior, the geometry, boundary conditions. So in a little cartoon, basically, we go from the design, from the architect, to an idealization of all these ingredients, so boundary conditions, loads, etc. As engineers, analysts, we try to look for first 2D models. So we try to look for example, plane stress conditions. We've seen the plane problems in the previous video. We've seen the plane stress, but there's also the plane strain. For example, plane stress, a thin structure where we can assume load the stresses and the solution to lie in one plane, or the plane strain problem, such a dam, a water dam, where we will just consider a section of this problem. Or there is also the axisymmetric type of problem. We didn't look at the theory of this, but it's sort of similar to these two, but we will not cover axisymmetric problems in this module. But basically we use the axis of symmetry to look at a 3D problem in 2D and solve it. So less unknowns, smaller problem, and faster solution. If this is not possible, then of course we have to move to a 3D model, and where we have to discretize and idealize load, etc. for the whole geometry. These are more expensive, computationally more expensive, they take longer, and but sometimes we just need to do 3D models when there are no symmetries or we don't fall in one of these three conditions. So once we have idealized our model, so we have our potato and we have identified our external loads, what we do? Well, we decompose the domain in a finite number NE of finite elements. So basically we mesh our volume. You've heard about finite element mesh. Well, this is usually done in a pre-processing phase of standard finite element codes, and something that is underneath our computer is usually the so-called Delaunay triangulation, is the way you generate a mesh automatically. And so we basically discretize our continuum, and we can have it finer in some regions of interest and less fine in others. In 2D, in 3D, for example, we can mesh this little rabbit. And in our course, we will use Gmesh, that is an open source mesher that is available in Apps Anywhere. I will post a video later on in the module to show an example of how we can mesh a simple problem, and in fact we will use this to create the input for our MATLAB finite element code. So moving on to, well, before that, just a couple of remarks about discretization. First of all, we can say that the quality of the solution increases with the higher number of finite elements. Okay, so regions with high stress strain gradients should and must be discretized with a finer mesh. Okay, if we want the solution to be of high quality. Examples include, we should look for example, near cutouts, cracks, point loads, abrupt changes of thickness, material interfaces, or entrant corners. So these are all regions we should look at and as modelers take into account, and we should refine our mesh in these regions. Second, we should avoid high aspect ratios. So basically skinny elements, we don't like them, whereas low aspect ratios are much better. Okay, this part we don't really control a lot of this. Commercial software deal with this already. They have very good measures, but in our simple FE code, we should look at this and make sure that the mesh we generate are not too skinny. Third, let's look for symmetry. Okay, conditions of symmetry can enable us to decrease the model. Okay, so for example, here we have two symmetry lines, and we could model this just by studying this little quarter, and therefore instead of using, in this case, 6 elements times 4, 24, we're just going to have a model of 6 elements, and therefore the number of unknowns are smaller. To do this, then we need to introduce the boundary conditions appropriately, okay? And we'll see some examples along the module. Finally, physical interfaces resulting, for example, in a change in material should be considered as an inter-element boundary. That is, we must not have elements crossing to different materials, but we should introduce an inter-element boundary here and therefore discretize this appropriately. I mean, here this is a schematic diagram. I have 4-sided elements, 3-sided elements. This is possible. It's just to show you that we need to discretize this physical interface. Okay. So moving on to the modeling part, the crucial part. Okay. As we have meshed our continuum, we can number our elements 1, 2, I, and E. And let's look at a single element I. In this case, it's a 3-noded element, but we have NE elements. And so element I with NM nodes. In this diagram, I've represented a 3-sided element. Okay, so with 3 nodes, 1, 2, 3. The dimensions of space D will be 1 in 1D, 2 in 2D, 3 in 3D. So D is a number that goes from 1 to 3, depending on if we're using a 1D model, a 2D model, or a 3D model. So set this, our final goal is to obtain a model of displacement inside the finite element I that only depends on the values of the nodal displacements. Okay? So, how can we do that? Well, let's represent this. So we want the displacement u in position x, okay? So in this point, I just put it here, but it can be anywhere inside the element. That is function of just the nodal displacements. Nodal displacement, this is a 2D diagram, so for node 1, ux of node 1, uy of node 1. ux of node 2, uy of node 2, ux of node 3, uy of node 3. Now, what's the displacement of this point here as a function of these 6 displacements? Well, you can imagine that you could interpolate the displacement from the boundaries and obtain something that is valid for inside the element. In fact, what we do is we introduce an interpolation matrix or a shape function, also known as, that basically tells us that the displacement inside our element, in any point inside our element, is equal to this interpolation matrix that multiplied by this nodal displacement vector. Okay, so 6 by 1 vector. So this nodal displacement vector, this is the shape function matrix, and again the dimensions of ux is d, the dimension of, so in a 2D problem, okay, this is 2 times 1, and then n is going to be 2 times number of nodes. So we have a 3-noded element in this case, so 2 times 6, and then the dimension of our problem is 2, number of nodes 3, 2 times 3, 6 times 1. So what is this nx? If you know this nx, you have the model of the displacements. Okay, let's see in general terms how shape function or this interpolation matrix is obtained. this is like the general procedure that we can follow. So the displacements of the element I, okay, are made function of a vector alpha I, which we don't know, a generic of generic parameters star. So we can say that u of element I of any point, so this ui is inside the element, is equal to a shape function star times alpha I, okay? Now, if this is the displacement in our element, then this displacement must be valid at the nodes. So what we do, we impose consistency at the nodes, at the nn nodes. So we say a displacement of element I in the coordinates of my nodes, so the node j, so for example in this point, in that point, and in that point, is equal to n in that location times alpha I. But what's the displacement at the nodes? Is the nodal displacement vector of element j. Is the nodal displacement vector at the nodes j1, 2, and n. So writing this down explicitly, we have u of element, so the displacement inside element I at the location x1, where x1 means in x and y, so because it still is a vector, is equal to ni star in that position, alpha u1, etc. So imposing this consistency, then we can then write that ui at the nodal locations is equal to a matrix psi I alpha I, but this is the nodal displacement vector, okay? So what do we do with this? Well, given this consistent condition, we can then solve these linear equations and obtain our alpha I, that is a vector that we didn't know, by inverting the expression that I just reported. So psi I times alpha I is equal to u of the nodal displacement vector. So alpha I is equal to psi to the minus 1. If you multiply psi minus 1 on the left and right hand side, this goes away, so you're left only on that. And in this way, if we then substitute alpha I into the original general formulation, you can then obtain that the shape function is equal to ni star times psi to the minus 1, okay? So this is how we obtain in general the shape functions, and they will depend on what type of unknowns and how we make them depend on x and y, so on the position. But we will see later with an example, and in particular with the constant strain triangle element, how this look like and how we obtain them. But this is the general way we can do it. Now, given the displacements inside of our element, then we can get the strain and stress and strains, because we have the model for the displacement. In fact, if you recall the plane problems lecture for 2D, but even the first lecture, we know that the strains is we have the definition of strains, that in the matrix representation we introduce this consistency differential operator. So epsilon is equal to cu, but we have a model for u, but this differential operator in 2D is represented here, but we have a model for u now. If we substitute the model for u, that is u equals to the shape function of element I times the nodal displacement vector, then we see that the strains inside our element are actually function of a B matrix times the nodal displacement vector. So this is the strain displacement matrix, and basically the strains inside our element is function of the nodal displacements. So given the strains, we know stresses using the element stiffness matrix. So stress is equal to d epsilon, but epsilon is BUE. So if we substitute again, stress is function of the nodal displacement. So in 2D problems, these are the dimensions: 3 times 1, epsilon x, epsilon y, gamma xy, 3 times 1, and then this is the dimension of the B matrix, okay? 3 times 2, the number of nodes of the element type you're using. So in case we are using a 3-noded elements, we have 3 times 2 times 3, so 6, okay? So moving on to the coordinate transformation. In some cases, the local reference, for example in this diagram here, of element I, which I rotated, is not the same as the global one. So in this case, what do you expect we'll need to do? Well, we need to do a rotation of the element, so we need a coordinate transformation. This can be done by using a rotation matrix. I believe you've seen this in last year with the direct stiffness method, but basically we can write the displacement of nodal displacement in the local coordinate system as function of the displacement of the global coordinate system through this rotational matrix. Okay, so given this, then it's straightforward that we can do for each element I, from 1 to number of elements, you can say that the displacement inside my element I in the local coordinate system will be equal to our shape function times this transformation matrix times the displacement, the nodal displacement of element I in the global coordinate system, okay? And given u, again, epsilon and sigma in the same way. Now, once we have the stresses and strains and displacements of our single elements, in fact, we need to rebuild the discretized solution into the full body, okay? And this is done by an assembly operation. So you see here element 1, 2, and 3, 4 joining back into our continuum well-discretized whole mesh body. And we see that, for example, this node in the global system, 1, 2, 3, 4, 5. So node number 5 in the global system is actually where nodes in the local system 2, 3, 2, 2 of these 4 elements join. So it's not efficient and not good to have all these nodes saved and their displacement saved because they are the same node in the global system. So what we do, we can define this global displacement vector, capital U, okay, from which we can then reobtain the displacement vector of our of each element I, okay, by using this Boolean operator, so a connectivity matrix that basically with true and false statements is able to not repeat the same information, okay. So for example, we will know that the global number 5 is representing the same information for the local 2, 2, 2, and 3 of elements 3, 4, 2, 1 respectively, okay. So this is what happens during the assembling. And so the sixth step is the stationarity of the total potential energy in discrete form. Why? Well, you should know by now that the stationarity of the total potential energy implies equilibrium. And so let's see and consider this single element here. So if we highlight and just look at it by himself, we can then introduce R as the stress vector on the constrained boundary gamma u, and Ri as the stress vector on the internal interface gamma I. So if we isolate this element from the rest of the mesh, these reactions between these other elements appear, and so we have this little poor element omega I with some boundary external forces, body forces applied to it, reactions at the boundary, and internal reactions at the interface. So if you look at the planes problem lecture, we define the total potential energy. So the total potential energy, which is equal to the elastic energy minus the external loads. So we can write it as and introduce our model in here. So epsilon d epsilon star, where epsilon is the differential operator applied to the displacements, etc. So if we do this with the model of displacement and strains we've just seen in the previous slides, then we can obtain the following expression for the total potential energy of the single element I. And by substituting the model for displacement as nu of the element, so the shape function, we then see that we get to this expression, okay? So B, the matrix B we've seen before, B dB, and then UL of the nodal displacement vector of element I comes up here, and all these other terms for the external energy, so the work over here. Now, again, this is the strain displacement matrix we've seen in the previous slide, the material stiffness matrix, and the shape function matrix, all function of the nodal displacement of element I. Okay. Now, with recalling this here, let's give some definitions to make this very long expression in a much concise and simple form. We define KIL as the stiffness matrix of element I in the local reference frame. So this integral here. We have the equivalent nodal load vector of the element I in the local reference frame, defined as this, okay? These terms over here. And then we have the equivalent nodal reaction vector, and finally the equivalent nodal internal reaction vector of element I in this local reference frame. So if we give these definitions and we rewrite the total potential energy of the single element, we see it has this form over here. So a half UIL transports KIL UIL, so it's U squared in a sense, minus PU minus RU minus R internal U. Stationarity of the total potential energy, if we do that, we get the first, so the first derivative, let's say, equal to 0 would imply equilibrium. And so if we do that, we differentiate this, we see that this was a squared term, so we have a half U squared becomes 2U, and then the delta U goes out. The derivative of that with respect to U is P du goes out, minor R du, etc. for all the U's. So if this is 0 for any delta U kinematically compatible displacement, virtual displacement, then we are in equilibrium. So in the end, if this is for any, then this must be equal to 0. And if this is 0, then we can write that K of the local element UL is equal to P plus R of the internal reactions. Okay, so now if we write the total potential energy for the whole FE mesh, we can see that it's basically the sum of, from 1 to the number of elements, of the total potential energy of element I. So if we write that, we introduce this for each I element. So the internal reactions will go to 0, because by joining them, this term sums to be 0, okay, because action reaction, and then by joining elements goes to 0. So if we substitute the displacement of element I in the global reference frame using the rotation matrix T, then we can define the stiffness matrix of element I in the global reference. So T transposed KT is the stiffness matrix of the element I in the global reference frame. And in the same way, the equivalent nodal load vector in the global reference and the equivalent nodal reaction vector in the global reference. So the total potential energy of the whole system of the assembled mesh will be the sum of, from 1 to NE of using the stiffness equivalent nodal load vector and equivalent nodal reaction vector in the global reference frame. Okay. At this point, we substitute the displacements of element I using the global nodal vectors, okay, using the Boolean matrix Li, and so we define K, P, and R as the global stiffness matrix of the whole system, the global equivalent nodal vector, and the global equivalent nodal reaction vector, okay? So the total potential energy in terms of the global displacement vector, U, is then equal to half U transposed KU minus PU minus RU. And therefore its variation, the first variation is equal to this. And again, remembering that the stationarity of the total potential energy equal to 0 would imply equilibrium through the PLV, the principal virtual work, then we can write that Ku is equal to P plus R is what imposes equilibrium conditions at the FE mesh nodes. Okay? So this is just a remark that if rigid bodies have not been eliminated, K is singular, so our structure needs to be restrained, and you should avoid a rigid motion of the whole system. Okay, sometimes in finite elements you forget to put the boundary conditions and this system can just float, so you can't invert it, so you can't get the solution. So the last step is the solution. How do we get the nodal displacements from that system of equations just represented? Well, first of all, we subdivide the nodal displacement vector U such that we have the free nodes and constrained nodes separated. Okay, if we do that and we put the free nodes at the top of this vector and the constrained ones at the bottom, then we can partition K, P, and R accordingly. So we will have the system that will look like this. So let's say KFF is for the free, and whereas KCC for the constrained, etc. So we partition the system and we have KFF is non-singular, so it will be invertible. Then we have the unknown U nodal displacement. Then we have the known constrained displacement, because they are either 0 or it's an imposed displacement if you have like imposed settlement. So there are no reactions in the free nodes, but then there are unknown reactions on the fixed nodes. And this is the nodal load vector, okay, due to the boundary loads, so pressure and so surface pressures or body forces they become nodal loads, equivalent nodal loads. So from the first vectorized equation, so this times that is equal to this, we can obtain UF by inverting KFF multiplying by P minus KFC UC. Now given UF, we can substitute it in the second, okay, and obtain the other unknowns, which are the reactions, RC. So where R are the nodal reactions, free and constrained nodal displacements are UF and UC. In this way, we've now obtained the displacements and the reactions of our global problem. How do we get stresses and strains? I'll reconstruct the whole set of unknowns. Here it is for each element, I to NE. From U, we can obtain the element displacement vector in the global reference, and then we can use the transformation matrix T to get the displacement vector of our inside each element in the local reference. And once we have that, we can calculate so these are the nodal displacement vector in the local reference. From that we can obtain the displacement inside each element using the shape function or our model for displacements. Once we have the displacement inside each element, we obtain the strains through the B matrix, and once we have the strains, we can get the stress once we know the constitutive relationship of the material. So for elastic materials, as we're going to deal with, we've seen this in the previous lecture for 2D problems. So this is basically it. This is the finite element method and how it works. So we've seen the idealization step. The architect gives us the drawing. We get an idealized model, okay? Then we discretize it. Well, this is a rabbit. I don't know how from a house I got to a rabbit, but you can make errors as engineers. Then we can model, so we introduce a model for displacements through the shape functions that basically tell us what is the displacement inside each element given the displacement from the nodal displacement vector. If we have a local coordinate system different from the global one, we need to transform and do some through the T matrix, and then we need to assemble our solution, do the stationarity of the total potential energy of the discrete form of the total system, and then obtain the solution, so the displacement capital U of our whole system. And once we have the total the displacement of all our nodes, we can reconstruct the whole set of unknown fields. So go back to the nodal displacement vector of each element, and from that we can get the displacement inside each element. And if you have the displacement inside each element, you can get the strain and the stresses. So with this, I have concluded, I would say, the core lecture of this module. And I thank you for being patient. I hope this was clear, but I'm sure that with the next lecture, where we will deal with the constant strain triangle element, the most famous and simple FE element is in fact the ones that you see here behind. Well, forget about the remeshing here that I use, but we will see practically what all the steps that we've just seen today look like, and you will probably learn all this, hopefully. Thank you. See you next week.